Hi there. This is lecture 17 of our course, Advanced Quantum Mechanics. Imagine a robot is throwing a ball. And the first throw makes it go a distance of x1 equal to 50 meters. And then the robot throws again the ball. And the second time, 50 meters. And the third time, 50 meters. So what's the average? Well, the average then of the robot's long distance throws is x1 plus x2 plus x3 over 3, which is 50 meters. That was the robot's average distance. This means that the square of the average distance is 2,500 meters squared. What, however, is the average of the square distances? Well, average squares, well, this is what we would write as x squared and then the average taken. So this is x1 squared plus x2 squared plus x3 squared, third, and this is also 2,500 meters squared, obviously. Now, if I throw the ball, so this was robot, right? Now, if I throw the ball, then it's going to be different because I'm not as accurate as the machine is. So maybe my first throw might be 50 meters, I'm lucky. But then the second throw might be 49 meters. The third throw might take it 51 meters far. Okay, I think you see where this is going. We calculate the average, and the average is, of course, 50 meters again, which means that the average squared is 2,500 meters squared. But what is, in this case, the average of the squares? Well, we have x squared bar. So this then is going to be 50 squared plus 49 squared plus 51 squared divided by 3. And this is 2,500 plus 2/3 meters squared. So what we have is that because there was some spread in the distribution, the average of the squares is not the square of the averages, of the average. So what we have here is that in this case, x squared average minus the average squared, which is also called the variance, of course, was 2/3 meters squared and therefore not 0. You remember, of course, that this is the behavior that we saw earlier in this course for quantum mechanics. We saw that in quantum mechanics, for observables f hat, we have that in general, if we take the observable and square it and calculate the expectation value of that, so the mean value of a run of experiment, the mean value of an ensemble of experiments, this is not going to be the same as if we took the mean value and then square it. And why is that? Well, that was because when we calculate these things, then in quantum mechanics, they are as follows. Psi f hat squared psi is this. And we can ask, is this the same as calculating psi f hat psi and then squaring that? Is it or is it not? Well, let's write it out in a basis, then it will become clearer. Because then we're just dealing with numbers and not with abstract operators and abstract vectors, but with just numbers. So in a basis, this equation is sum over I and j, and then psi I star, f hat ij, f hat jk, psi k. Just insert a resolution of the identity in some discrete bases here and there, and then work it all out. You should get this. And then the question is whether this matches what we get when we take the sum over, let's say, R and S, and then psi star R, f hat Rs, psi S, and then square the whole thing. And now it's clear that that's generally not true. It's generally not equal. So therefore, those two don't match and we have a variance. And we concluded, therefore, quantum mechanical, in fact, quantum theoretical predictions, and the distinction is that quantum mechanics is about individual single particles, I mean, one particle or maybe a finite number of particles that cannot be destroyed or created. Quantum theory is much more general. It includes also the quantum theory of fields, and then particles can be destroyed, and it can be described how to destroy and create particles. The argument that I'm just making here is true for both quantum mechanics and more generally for all quantum theories. So quantum theoretical predictions generally have delta F not equal 0, and therefore are probabilistic. There's going to be some spread in the outcome of the measurements. Now, while this argument is very important, it leaves a loophole. You see, even the classical theory can have a spread, like in Las Vegas, where their business is uncertainty and they're not using quantum mechanics for it. So in classical theory, you can also have uncertainties simply by doing things inaccurately, like when I throw a ball, or when an engineer does a not so great job of keeping track of where things are going. Then there's going to be uncertainties. And one could imagine that in quantum theory too, in principle, those uncertainties might be there, but maybe they can be removed. If you just choose your states right and prepare things right, then maybe there wouldn't be uncertainties. But it turns out that these uncertainties are unavoidable. These uncertainties are unavoidable. You see, with the argument above, we only show that they generally occur, but that leaves open the loophole that they might be avoidable, namely by choosing your psi's and f in a very fine-tuned way so that there are no uncertainties. Maybe you can cook up some systems just without any uncertainties. It turns out, no, you can't. Uncertainties are unavoidable. And you know, of course, from a prior course in quantum mechanics, that we have the fundamental uncertainty principle. And this means that even the best engineers cannot make both delta x and delta p go to 0. So ordinarily, in classical mechanics, you could. You can know where something is and how fast it is, but quantum mechanics prevents that. So therefore, we must have fundamental probabilities in quantum mechanics. Are we done with that? No. There are more questions of a fundamental nature that need to be asked here in this context. More questions follow. First of all, one question is, can there be hidden variables? That determine the seemingly probabilistic outcomes. See, this potentially offers a loophole here. It could be that beyond the framework of quantum mechanics, there is an extension of quantum mechanics which has some hidden parameters in it, some extra variables that are not visible if you just work with quantum mechanics. And these parameters are just classical. And they, if only we knew them, they would determine the outcome of the individual measurements. Einstein was a believer in that. But it turns out that, well, in general, the community thinks that, no, there are no hidden variables. The full story is that, yes, there could be hidden variables, but then there's a price to be paid for that, which is that nature has to be fundamentally non-local. And in principle, there's a choice. You can either believe that nature is fundamentally non-local, meaning that there is action at a distance in some weird fashion that we don't really have a mechanism for, or we have to accept that there are no hidden variables and the probabilities are indeed fundamental, which means that nature fundamentally does some gambling, where things happen without a reason. Both are hard to swallow, namely that nature is non-local, is hard to believe, or that nature just does things without a reason. For example, when a nucleus decays. According to quantum mechanics, it has no reason when it does decay. There is a reason for its half-life time, but when exactly a uranium nucleus decays, why it decays now, not 5 minutes later, is fundamentally undetermined. Anyway, we will come back to this question of this alternative, namely that either there are hidden variables, but then nature has to be non-local, or there are no hidden variables, then nature just is able to do things without a reason, without a cause. With probability distributions, of course, it can be calculated, but the individual outcomes would not have a cause. All right, that's one thing that we will cover later in this course. In the context of the EPR formalism and experimental predictions for that, and the and measurements and the notion of entanglement. Secondly, there is the possibility that not only can delta x and delta p not be simultaneously known, but it could also be that delta p alone cannot be made arbitrarily small, and delta x alone cannot be arbitrarily small. And that could be because of gravity. Does gravity impact the uncertainty principle? You may wonder, why should it? How is gravity different from any other force, like the electromagnetic force or the weak force or the strong force? Well, it is different in a very fundamental way, as we will discuss later, and that could make it interfere with the uncertainty principle in a fundamental way. All right, before we get to this, let us reconsider where the uncertainty principle comes from. So, where does delta x, delta p larger equal h bar half come from? Well, here's a proposition. The proposition says, for any two observables, f hat and g hat, we have this general uncertainty principle, namely delta f, delta g is larger equal to 1/2 absolute value of the expectation value of the commutator of f and g. That's the most general uncertainty principle. And the special case is this one. Special case. F hat is equal to x hat and g hat is equal to p hat. And then, of course, we have that this uncertainty principle in red becomes delta x, delta p larger equal to 1/2 absolute value of the expectation value of the commutator between x and p, but the commutator is I h bar identity and psi. And now we see that this is equal to, well, I h bar psi psi, and of course this is equal to 1. Notice that the general uncertainty principle is state dependent, depends on psi. But the basic uncertainty principle between x and p does not, because at this point it drops out, because all our states have to be normalized, and therefore this is always a 1. So what we obtain is that delta x, delta p larger equal to 1/2, and then this h bar comes out of the absolute value just as an h bar, but the I gets stuck and the absolute value doesn't come out. So we have the uncertainty principle. Now let's prove this proposition. This is a super important principle. You can use it everywhere in quantum theory, the uncertainty principle in red. So let us prove it so that we are clear about where it comes from. So proof. Well, of the uncertainty relation. So we start with the observation that we know that for any state phi, we have that its length, for any Hilbert space vector, its length has to be larger than 0. And now we choose phi to be the following vector. We choose it to be f hat minus f bar identity plus I alpha, alpha being an arbitrary number, g hat minus g bar, and we apply that to some arbitrary state psi. Okay, so f hat and g hat are the operators for which we want to calculate an uncertainty principle. Psi is an arbitrary state, and alpha is arbitrary. Arbitrary complex number. Later we will make a good choice of alpha, but for now we will keep it arbitrary. So the statement that the length of the vector phi is larger than 0 is now this statement. So therefore we have that psi. So I just take the complex conjugate, the Hermitian conjugate of this vector, put it to the left and then the vector to the right and say that this is larger or equal to 0. So it's all very easy, even if it's a little bit tedious. So it's f hat minus f bar, the identity, minus I alpha, because I'm taking the Hermitian conjugate here, minus I alpha, g hat minus g bar, identity. See, it's g bar is a number, right? It's the expectation value of g. Therefore, I put the identity operator here because the whole thing is in terms of operators. And this is multiplied with our vector phi. So this is literally just what we have up here, minus f bar identity plus I alpha g bar minus g hat g bar identity and psi. This is larger equal 0. That's true for all psi and it's true for all alpha. So this can be spelled out and we obtain that we get the following terms. We get this term times that term. We get this term times that term. And then we get the mixed terms as well. So what do we have? We have psi, and then we have f hat minus f bar identity, and squared, and psi. So this is the term where we have this bra contracted with this ket. Contracted with is another word for, is another terminology for taking the scalar product with. Okay, and we get another term, plus, and that comes from this term times that term. So this is alpha squared, because we have minus I times A, minus I times I, that's a plus 1. Alpha squared G, I forgot to open the inner product here. So it's alpha squared psi, and then g hat minus g bar 1 squared psi, and mixed terms, plus alpha psi I, and then it's f hat g hat minus g hat f hat psi. All of this is larger or equal to 0. Okay, so we recognize here that we have here the uncertainty, the variance in f, and here we have the variance in g. So, i.e., we have that the variance in f squared plus alpha squared, the variance in g squared plus alpha psi I commutator of f hat and g hat, and then psi larger or equal to 0. Now let us complete the squares so that we don't have an alpha squared term and the term linear in alpha. Instead, we will write it as alpha minus something squared. So we are completing the squares in alpha. So completing the squares. Then what we obtain is that delta f squared plus delta g squared. And now we get this big term, alpha plus. And then here in the denominator we have 2 delta g squared. And in the numerator we have psi I commutator of f hat and g hat and psi. All of that squared. This produces, of course, the term delta g squared alpha squared, that's this one, but it also produces the mixed term, where we have this times that, right? We have the delta g squared goes away, and so we obtain that term as well. And then we also have to subtract now the superfluous extra term that arises by having this squared now. So we have to subtract here psi I commutator f hat g hat psi squared divided by the denominator squared, 2 delta g squared squared larger equal to 0. And delta, sorry. That's delta g squared larger equal to 0. This holds for all alpha in C. We didn't have to make a choice just yet. Now, is there a good choice for alpha? You see, what we really are after is an uncertainty principle for delta F and delta G. And we have already an uncertainty principle for delta F and delta G with this equation. But it's a different uncertainty principle for every choice of alpha. Now, the uncertainty principle means that these terms here together have to be larger than 0. Now, imagine what happens if we choose our alpha to be 10 quadrillions. Well, if alpha is really large, then this is a really large term, and therefore, you know, delta F and delta G, I mean, for the left-hand side to be larger than 0, we have little constraint on the delta F's and the delta G. It's easy for them to fulfill this. How can we make it the hardest for the uncertainty principle to be fulfilled? Well, we make it the hardest by making that positive term as small as we can. And we can actually make it 0 by choosing our alpha to match that quantity here. So if we do this, choose alpha equal to minus psi I f hat g hat psi squared over 2 delta g squared. You may wonder, wait a moment, is this thing really positive? Is this really positive? How do we know that this is positive? Isn't there an I in there? Okay, so you can show that this commutator is anti-self-adjoint. I times the commutator is self-adjoint. And then we're calculating an expectation value of it. That's a real number, right? And then we square it, we get it positive. So in any case, the point is we can choose our alpha to be this value, right? We can certainly, no matter what else we argue, we can choose alpha to have this value. Then our uncertainty principle here becomes delta f squared plus, well, that whole bracket here is now gone. If you obtain that, delta f squared minus, and then we have here psi I commutator f hat g hat psi squared divided by 4 delta g squared, because we have a delta g to the 4th here, and here we have it squared. All of this is larger or equal to 0. Therefore, we have delta f squared. If we multiply the entire equation with delta g squared, we obtain delta g squared here is larger or equal to, now we throw that on the other side, 1/4, and then psi I commutator f hat g hat psi squared. Now, as we already said, this is a self-adjoint operator. This expectation value is real, and this is the square of it. So therefore, we obtain that we can take the square root of this entire equation here, and we obtain delta f, delta g, larger or equal 1/2, absolute value. See, we take the positive root of this, of course, because the left-hand side is positive. And then it's 1/2 absolute value psi, and then the I doesn't matter when we take the absolute value, and then we have f hat, g hat, and psi, and that's the generalized uncertainty principle. Now let's come back to one of the loose ends that we discussed earlier. Namely, remember, the uncertainty principle, the uncertainty relation between x and p in quantum mechanics normally looks like this: delta x, delta p, and we have delta x, delta p, larger or equal h bar half. And we can also write this as delta p larger or equal h bar over 2 delta x. And that means that delta p, if we look at the equation delta p equal to h bar over 2x, we get a hyperbola. That looks like this. It's asymptotic to this axis, asymptotic to that axis. This is the line delta P equal to h bar 2 delta x. So all of this here is the allowed region. And this is disallowed. In quantum theory. So there are no states in there. However, according to this standard uncertainty principle, delta x can be made arbitrarily small, right? We can go here, for example, and we would have a very small delta x. Of course, the price to pay would be that in order to be in the allowed region, we would have to be very high up over here. So delta p would have to be very large. And vice versa. Delta p could be made arbitrarily small at the cost that delta x would have to be very large. Now, we concluded earlier that quantum mechanics provide some fundamental uncertainties in the sense that delta x and delta p cannot simultaneously be determined with arbitrary accuracy. But could it be that they can be determined with absolute accuracy individually? According to this uncertainty principle, yes. But can they really? Can delta x or delta p go to 0 individually? Yes. According to this uncertainty principle, yes. But really? It's not clear. Gravity may interfere. May interfere. Again, let me come back to that question that you may ask at this point. What's special about gravity? If gravity can indeed interfere with the uncertainty principle, well, then electromagnetism should be able to interfere, and the weak interaction and the strong interaction. And then I said, yeah, but gravity is different. Gravity is not an ordinary force. And here is why gravity can interfere with the uncertainty principle and may make it impossible for delta x or delta p, even individually, to be made arbitrarily small. So why? Why could gravity interfere? Well, first, briefly, is delta p going to 0 possible? Well, recall, gravity curves space. Now, fixed momentum, this is all very hand-wavy. What I'm saying can also be made accurate. You can calculate these things. And I've myself published also on that. But roughly speaking here, what we have is that for delta p going to 0, we have sharp or, yeah, a sharp velocity. Right? If we know the momentum absolutely accurately, then we should know the velocity absolutely accurately. Which means we should be able to tell it's going to go this straight line. But in a curved space-time, where there's gravity, where there's curvature, there is no such thing as a straight line. You see, on a surface that's wobbly, there is no such thing as a straight line. Even straight lines, namely, the best approximation to a straight line, a geodesic, is not really straight. It's curved. And therefore, you may have the delta P cannot be made arbitrarily small in the presence of curvature. Geodesics are not straight lines. Now, it is not, a lot of work has gone into formulating quantum theories on curved space-times. But it's not really clear what happens to momentum on curved space-time. I was part of a collaboration that even proposed some experiments that would measure things like this to see whether curvature can impact the propagation of wave functions in such a way that there is a fundamental uncertainty in momentum. At the moment, we are not experimentally ready to measure these things, but it's an interesting possibility. Secondly, and that I think is even much cooler. Secondly, we can ask, is delta x going to 0 possible? Again, gravity may prevent it. Again, why would gravity interfere here? Well, let me tell you the fundamental reason why it can do that. The fundamental reason is the Einstein equation. The Einstein equation looks like this. G mu nu equal to kappa T mu nu. If you haven't done general relativity yet, never mind the details. I'll tell you what matters here. This quantity here is a tensor field, and it describes the curvature of space-time. It's the Einstein tensor. This thing here is also a tensor. Oh, that's just a constant, gravitational constant number. And this is the energy momentum tensor. And roughly speaking, it contains E and P. They're just arranged in this tensor. Oh, what happened here? Okay. Now, why did I bring up the Einstein equation? Remember, the question is, can we really make delta x arbitrarily small? If we had arbitrarily good instrumentation, could we do it? It turns out the Einstein equation is interfering with it. And here's why. Assume we want to measure a small distance. Distance x. So here's the point, there's a point, and we want to know the distance between them. Now, obviously, we need a delta x that's smaller than x, right? So we need a correspondingly small delta x. So let's say we want to build a microscope that does this, and we want to hire the best engineers so that they can make delta x arbitrarily small. So engineers do this. They make the machinery more and more accurate in order to make delta x smaller and smaller. Now let's just say engineers. Let's say they make delta x smaller and smaller. Let's just naively assume that this is possible. Well, then delta p grows by the uncertainty principle. But see, in the Einstein equation, we have the energy momentum tensor here and the curvature there. See, the Einstein equation is expressing how matter is curving space. Matter is the energy part of the energy momentum tensor, but the momentum part of the energy momentum tensor also curves space. Energy and momentum in any case can transform into each other by Lorentz transformation. So the Einstein equation tells us that given some energy and momentum distribution, it curves space according to that equation. And that also means, or at least it should mean, that when the energy and the momentum are uncertain, well, then the curvature also ought to be uncertain if the Einstein equation holds. But that means that if delta p grows, we must have a growth in the uncertainty of the curvature, right? Uncertainty in p means uncertainty in t means uncertainty in the curvature. So this should mean that the uncertainty in t mu nu grows. And then by the Einstein equation, and so we have, roughly speaking, an uncertainty in the curvature that grows. But you see, this is alarming, because if the uncertainty in the curvature grows, and by the way, only gravity can do that, right? Electromagnetism doesn't curve space, but gravity is the curvature of space. There's no analog to the Einstein equation for electromagnetism or any other force. So what we have here is an alarming behavior now, because you see, the engineers set out to make delta x smaller and smaller so that they could resolve the distances that are smaller and smaller. But as a consequence, delta p grew, delta t grew, and delta g is now growing, which means that in this region, the uncertainty in curvature is growing. But you see, if there are 2 points, and between them, the curvature of space is uncertain, then the distance between them must also be uncertain. You see, if there's a big bulge or big hole between the 2 points, that makes a difference as to their distance. So if the uncertainty in curvature grows, as it has to, then delta p should grow. Not delta p, delta x grows. So we run into trouble here. This means that engineers can, of course, make the accuracy in measurements better and better, but eventually, the uncertainty in momentum will have created an uncertainty in the energy momentum tensor, which will have created an uncertainty in the curvature, which is large enough to prevent any further accuracy gains, because we would pay for it with curvature uncertainty, which means we can't really measure the distance very well anymore. And calculations show that if we take the two ingredients that we had here, the uncertainty principle and the Einstein equation, then we should have, or nature should have, delta x minimum of about 10 to the power minus 34 meter, which is the so-called Planck length. Now, that means that gravity can interfere with the uncertainty principle. But that would mean that gravity could interfere with the equation that delta x larger equal to h bar over 2 delta p. Remember, that was the uncertainty principle here. Delta x, delta p. Because gravity could make it such that there's a gap here, and there's a gap there, that delta x cannot be made arbitrarily small, not be made arbitrarily large. Sorry, delta p, x cannot be made arbitrarily small, delta p cannot be made arbitrarily small. And in particular, delta x it may not be possible to make delta x arbitrarily small, which means that space-time has some fundamental fuzziness, has some fundamental fluctuations in there. Some people would speak of a space-time foam. And how would that impact now quantum mechanics? Well, it turns out that in the literature, it was proposed that therefore the uncertainty principle should be modified a little bit. Namely, that we have delta x, delta p larger equal to h bar half, and then 1 plus beta delta p squared plus possibly higher order terms. But the idea would be that this is sort of a Taylor expansion of some unknown physics, and that is the lowest order term. And this would be small positive number. And you may remember this from an exercise that we did. So, for example, Witten and others published on that. And they were suggesting that this may also be motivated from string theory and general other quantum gravity considerations. And this is also called the generalized uncertainty principle. And it's abbreviated GUP. Now, one can show that with this generalized uncertainty principle, there's a finite minimum uncertainty in position, which is h bar square root of beta. So the idea would be that nature has this fundamental constant beta, such that delta x minimum is the Planck length of 10 to the minus 34 meters. Now the trouble is that, or trouble was, that from this argument here, all you got was an uncertainty principle. And with that, you can calculate uncertainties, but that's all you can do. But it would be very interesting to actually be able to calculate the quantum mechanics that comes with this. Because obviously this has to interfere deeply with quantum mechanics. Something must be very different when you have that, because delta x minimum not being 0 should interfere with various things. For example, x, the position operator, should not be self-adjoint, as I will show in a moment. Okay, but in any case, the question that then arose And that was a question that came up when I did my PhD, is what's the quantum mechanics? What's the generalized quantum mechanics? And the answer is very simple in hindsight. Namely, what you will have is that the commutation relations have to be of this form, plus beta p hat squared plus possibly higher order terms. But the higher order terms would be very small. Now, that's easy to write down, but you'll have to find Hilbert space representations for those x hat and for those p hat. And so you have to start from scratch, right? Remember that we found x hat, p hat representations in terms of those infinite by infinite matrices, and then we found them in terms of these multiplication and differentiation operators with the Dirac delta and all of that stuff. Have to do all of that over from scratch. And so then need Hilbert space representations. And once you have those Hilbert space representations, then you can calculate, of course, everything. Then you can do the harmonic oscillator, the hydrogen atom, or whatever, using these commutation relations where the beta incorporates an attempt at taking into account what gravity will do. And if beta is very small, of course, then the corrections would be very small. Anyways, that was my PhD. Basically, I happened to be in the right place at the right time and figured out that this is the commutation relations that one needs to consider, and figured out what the Hilbert space representations are. And I was super lucky. People liked this, and even today, many years later, about 2 papers a week appear where people continue to work on that and work out the one or the other thing. You know, how do neutron stars behave when you put a beta in there? How does the absorption spectrum of hydrogen change when you put the beta in there? And you know, all of those things. Anyway, so this arose from my PhD. Actually, in my PhD, I had laid the functional analytic groundwork, and then I actually figured it out like weeks after I had finished my PhD. Then that's when I figured it out. Okay, so then what difference does it make? Remember, we spent a few hours on representation theory. And so now I can tell you what, you will find it easy to understand what is going on here. What's the difference? Difference to QM without beta? Well, see now, with beta, x hat is not self-adjoint. How do we see that? Well, assume f hat is self-adjoint, and f hat could be the position operator, but we can make the argument more generally. Assume f hat is self-adjoint. Therefore, there exists approximate or actual f eigenstates. Then, what is delta f squared in the state f? Well, it is the f expectation value of f hat minus f bar squared f, right? I mean, it would be for the position operator, it would be this. It would be x hat minus x squared x. This is delta x squared. And well, this is 0, of course, right? Because if x is an eigenvector to x hat, then it will just produce the eigenvalue, and the eigenvalue is also the expectation value, so the whole thing is vanishing. So this is 0. So what we see here is that when an observable is self-adjoint, then its uncertainty can always be made arbitrarily small by the spectral theorem, because by the spectral theorem it has eigenvectors or approximate eigenvectors, and in either case the variance is 0. So having seen now that gravity could make delta x minimum finite means that x, the position operator, is not self-adjoint. So what is x then? Then x hat is only symmetric. So what is a symmetric operator? Definition. An observable f hat is symmetric if psi f hat psi is a real number for all psi in the domain of our operator f hat. See, this is the minimum requirement that we want of an observable, namely that all its predictions come out real numbers. That's certainly something that experimentalists would insist on. They don't measure imaginary numbers, right? So f hat, an observable, is symmetric if the expectation value is real for all states in its domain. And we have in finite dimensions, finite dimensional Hilbert spaces, that f hat symmetric is equivalent to f hat being self-adjoint. But in infinite dimensional Hilbert spaces, that's not the case. In infinite dimensional Hilbert spaces, we have that it only goes in one direction. F hat symmetric is implied by f hat self-adjoint, but not the other way around. Okay, so you may think, all right, okay, so what? Well, it means on one hand that the spectral theorem doesn't apply, because the spectral theorem requires that an observable is self-adjoint. If it's only symmetric, too bad, no spectral theorem. But that's important here, right? Because we don't want to have a delta x minimum that's 0. Delta x minimum is possibly finite. But this also has a, and this has implication. This has a fundamental, it has opened up the window to something important. Namely, it turns out that the delta x minimum, which is finite, means, and this functional analytic issue here, that symmetry is not the same as self-adjointness, that is at the heart of it. Delta x minimum finite means that psi of x is band limited. You see, you may know that band limitation means from communication engineering that there are only frequencies up to a certain band limit. And that's what you get when you have a finite minimum uncertainty in some variables such as x. And that has opened up the window to now bring in all sorts of information theoretic methods into quantum mechanics. Because once you have band limitation, then you can quantify how much information is flowing this way and that way, and how it transforms, and what is information density and things like that. Okay, I went off on a tangent today because I find this stuff super interesting. Of course, you're not going to be examined on this business with beta and quantum gravity, because this is, of course, just an ordinary quantum mechanics, not on quantum gravity. But I hope you found it interesting too. Okay, see you on Monday. Have a nice weekend.